Hi, today I'm going to be reviewing with you some strategies for problem solving in chemistry. And probably the most fundamental is some math techniques that you have learned probably in middle school or early high school. Specifically today I'm talking about writing numbers using scientific notation. Um, so this is a skill that we will not only need to be able to do, but also understand throughout the stoichiometry unit um, and in subsequent units in chemistry. So just wanted to outline some real quick things here in terms of why we're even talking about this and why we do it in science. In science, we make measurements for a variety of different things. We might take mass measurements using a scale or a balance of some sort. We can take volume measurements, as is seen in the picture there with that scientist and his nice little what's called a graduated cylinder, usually measuring liquids. Mass measurements can be made using liquids or solids. We can also measure the volume of gases, so that's something there. We make instrument measurements, um, a variety of different types that give us numbers. And generally in chemistry, because we are usually referring to molecules and particles and atoms, we're talking about things that are so very, very small, that the numbers we actually arrive at are not usable numbers in common math practices. So what scientific notation is actually it's a short form of shorthand, and then any number can be expressed then as a product of two numbers. The first number you'll see is called the coefficient, and typically this number is between 1 and 10. It's between 1 and 10 because the decimal point is always going to go after the first number. Okay. The other piece that we have here is called the exponent. So you're multiplying by some 10 power of 10, whether it's an exponent, a positive exponent or negative exponent. We will talk about that in a little bit. But what scientific notation allows us to do is represent very large or very small numbers in a form that's more usable to us mathematically speaking. So you can see here how the number 0.00133 can be transformed into a much more usable number by moving this decimal place 1, 2, 3 units to the right and basically making a new number 1.33 and then tacking on that exponent to explain to the reader or whoever is referring to your measurement exactly how many places you moved to the right. So there's some general rules with scientific notation, the first of which is if the number that you're working with is 10 or greater. So we're not necessarily talking about positive or negative here, but if you're talking about anything higher than 10, so 11 all the way up to 10,000, it doesn't really matter. If the number is greater than 10, the decimal point has to move to the left. Looking at just some examples here quickly, and these do actually come from your practice worksheet. You would move the decimal, in this case, 2 places to the left, because you always want to move that decimal point after the very first digit. So in this case, you would be moving the decimal point in 377 to the left twice to get the number negative 3.77 times 10 to the second power. So the exponent piece of this, the power of 10, when we are a large number, is always going to be positive. It tells us that the number was big. Okay, if we have something as big as 8,000 or negative 8,125, we would move that decimal point 1, 2, 3 places to the left to get 8.125. That decimal point's now in a different spot, and instead of having 10 to the second power, we have moved our decimal point 3 places, so our exponent is going to be 10 to the third. And you'll see then how that instead of expressing a long messy number, we can do it very short and simply. You'll also notice that we don't drop off any of our units. So just because we move the decimal place does not mean that at any time we ever lose the rest of our numbers. Those numbers are still important, and I will talk about them in the context of the significant figure lesson. Okay. If your numbers are smaller than 1, that is all decimal numbers. The decimal has to move to the right in order to get it after the first non-zero digit. So if we look here at this first number, 0.041108, we would go ahead and move this decimal place 2 positions, so it's in between the first two non-zero numbers. Our new number then is 4.11, and our exponent, not sure if you could see it behind the frame of my video here, is times 10 to the minus 2. Okay, I'm going to actually rewrite that just in case you can't see it. Times 10 to the negative 2. So the powers here for decimal units are always going to be negative. It tells us that the number was smaller than 1. So if you can remember that negative sign being smaller than 1. In a very, very small number like 0.0009 and some change, we would go ahead and move this decimal place 1, 2, 3, and 4 positions to the right. So our exponent is going to be times 10 to the minus 4, because we have we started with a decimal number, so the exponent's going to be negative. We moved that decimal place 4 places, and the number we end up with is just now 9.8. Again, you can see how all of these numbers that we've arrived at are between 1 and 10, because we're always going to have a decimal place after the first digit. In this last example, again, we have 4 zeros after the decimal place, 2.1998. We're going to move this one over 1, 2, 3, 4, 5 places in this example. So our scientific notation exponent is going to be 10 to the minus 5. And the number we start out here with is minus 2.19. Okay, so now you answer a question for each of these. Try to jot this down, and then I'll explain a little bit. These are just the rules sort of outlined for you up here, remembering if the number is 10 or greater to begin with, as is in the case of 84 and 84,000, you want to move that decimal point to the left, and the power of 10 will be positive. If the number is smaller than 1 in 84 hundredths and 84, I don't know what that is, 100 thousandths, you're going to move the decimal point to the right, and the power of 10 will be negative. Okay, so these would be positive because they're above 10. We would move 1 place to the left. Here we would move 1, 2, 3, 4 places to the left. And in this case, they would both be positive because the number started greater than 1. The other two, however, would be negative because we're moving the decimal point to the right in both cases, either 1 or 1, 2, 3, 4, 5 positions. And the decimal point would then be negative to tell us that the number was originally a decimal. Now, to figure out what the exponent is, all you have to do is remember to count how many places you move the decimal point. Powers of 10 serves the basis for the metric system, so we do use this a lot in chemistry. If we start here at the ones place, you can see that 10 raised to the power of 0 is just 1. So if you have a 1-digit 1, 2, 3, 4, 5, all of those numbers are raised to the power of 0 times 10 to the 0. However, when we increase that exponent by 1, 10 to the 1 is equal to 10. 10 to the 2 is equal to 100, 10 to the 3 is equal to 1,000. So you can see how the way this works in the powers of 10 is that the exponent is equal to the number of zeros following the 1. So it tells you basically how big that number is. And in decimals, it does exactly the same thing, except it tells you how many zeros are to the right hand of the decimal place. So if we look here in tenths, we have the decimal point right in front of the 1. There's only 1 position to the left. Here there are 2 positions in 10 to the minus 2. Here there are 3 positions after the decimal point and minus 3, and so on and so forth. Okay, so if it helps you to go back to the powers of 10 to figure this out, by all means you can do that. I'm going to take just a break here real quick and ask you to figure out briefly what the exponent will be in each of these examples. Given the numbers 84, 84 hundredths, 84,000, and 84 hundred thousandths, I think that would be. We're going to figure out what the exponent would be in each case. So what do you think it would be for 84? Okay, hopefully you can recognize that the decimal point would originally be after the 4. We would move this only one place to the left, so the answer here would be A. The exponent would be 8.4, and the number, sorry, would be 8.4 times 10 to the 1 power. Okay, how about the second one? Okay, here we have a decimal to the left, and so we need to move it to the right. This is a decimal, starts out as a decimal. That means it's a smaller number. We already said this is going to be a negative exponent. The number is going to be 8.4 times 10 to the minus 1, because we moved it one place and we had to move it from being a decimal, so it's negative. For 84 thousandths, or 84,000, we would start with the decimal over here, go 1, 2, 3, and 4 to reach a number of 8.4 times 10 to the 4th. Because we've moved that position 4 times, it's a positive exponent because the number is greater than 10, sorry. Greater than 1. No, greater than 1. And here again, we move that decimal point 1, 2, 3, 4, and 5 positions. There isn't even an answer for that here listed. 8.4 times 10 right to the minus 5, because this is a very small number, much less than 1. So we get a negative exponent. We've moved that decimal place 5 places, and you can see here that the thing all these numbers have in common in scientific notation is their actual value, 8.4. It's the exponent that makes them different, and it tells us how big or how small that number really is, and where that 8 and 4 is relative to the decimal point in the original number. Okay, trying a few more. Whenever you see any number and there is no decimal place, you assume the decimal point is at the end of the number. So quickly going through here, we would go 1, 2 positions to the left. That would give you a final number of 5.20 times 10 to the 2, because we moved that decimal place 2 places, and it's larger than 1. Let's do all the larger than ones first. 520,000 would become 1, 2, 3, 4, 5. So we get 5.2 times 10 to the 5. Because we've moved it 5 places, it's bigger than 10, or than 1. Sorry, I keep doing that. 5,200 is 1, 2, 3 positions to the left. The number is 5.2 times 10 to the 3rd. Again, are you noticing that each of these numbers ends up to be the same in scientific notation, except for the exponent? That's what makes them different. It tells us the magnitude, the size of the number. Okay, and one quick example of a decimal, we go 1, 2 places to the right instead of the left. We still get a number of 5.2. We multiply that by 10 times a negative 2. That tells us that it was a decimal point. It was a number smaller than 1, and is much different, for example, than 5.2 times 10 to the 2. Okay, I have a variety of questions here you can answer or attempt to answer. Some of them did or will come from your worksheet. Which of the following is the correct scientific notation for 78 thousandths? That answer is going to be C. You can work this out in your own time. It's more of an answer key for you. You're always going to make it not 78, but you're going to put that decimal point between the two non-zero digits. 77.8 times 10 to the 4. For this number here, 9 thousandths, the final number is going to be, the answer is going to be 9 times 10 to the minus 3. For 2800, again, we want to rule out those answers that just give us 28 and now look at 2.8 as the best answer here. It's a number higher than 1, so our exponent is going to be positive. Oh, and I had a whole slew of examples, but I'm totally running out of time. So hopefully this was a good primer, a good help for you on scientific notation. If you need some extra help, I do have some videos from the Khan Academy I can share with you. Just get in touch with me and